All right. So, half a day and welcome, everyone. In fact, this introduction here, I was expecting to be done by our students. There are two students who are doing our seminar course here in the Sustainable Agriculture, Food, and Natural Resources program that is under the Agriculture and Life Sciences. And we are doing this sort of core seminar course, which is part of the graduate program. And included in that is setting up a series of lectures where we can invite guests to do it. And since COVID, we really have taken advantage of doing this online. And hopefully, like now, it's good to be able to spread it and get more audience to also join in. And I hope you will find it interesting and also be able to engage. So very warm welcome to all of us here. And let me introduce the team here. Myself, Dr. Mike Kabuki. I'm um, part or co-instructor of this course. And also I'm the interim associate dean here at the College of Natural and Applied Sciences. And along with me is Dr. Liu. And I'm not sure whether you are here, Dr. Liu.
Yes,
Okay.
I'm here.
Yes, introduce yourself, Dr. Liu, please.
Oh, hello everyone. I'm Dr. Zhenhong Liu. Feel free to call me Dr. Leo, um, or just call me Leo. My background is in animal science, slash meat scientist, and I am the instructor for this seminar course. Thank you everyone so much for joining our webinar series. I hope that I'm sure that we're all very interested with Dr. Barry Kim's topic. That's why we're all over here, joining. So
Yep.
without further ado from my end,
Thank
I,
you.
I think we could let Dr. Barry Kim take the floor.
Very good, very good. Before Dr. Kim, okay, I mentioned that can you just shout out from where you are, where you are joining from? Just very quick. Let's do that within the next a minute or so. Let's do this and open the floor. Thank you.
Okay, so I'm joining in on campus, office 105, CNAS over here at the extension side. Yeah, that's.
Okay. Okay, let's begin from those who are outside EOG, as I mentioned, please.
mm.
Okay, I'm Paul Kemp, Assistant General Manager at Guam Waterworks, and Barry is talking one of my favorite subjects here.
Hi,
Wonderful. Thank you.
I'm Dr. Weir, a local physician who has been worried about the effects of our pollution here in Guam.
I'm,
Wonderful.
I'm Vanjilu Han, the Senior Regulatory Analyst for GWA, and I work with Mr. Kemp.
Thank you.
And I'm Kathleen Moreland, recently retired from the Research Corporation of the University of Guam. And I'm here as a concerned resident, but also as a member of the Guam Environmental Protection Agency Board. Thank you.
Hey, Kathleen, thank you. Yes, yes. Anyone else?
John O'Connor from the Guam Daily Post is here as well.
Thank you. Welcome,
Window
John.
Win from AECOM in Honolulu. I actually work with Dr. Kim for a while. I'm also kind of work for a contract with NIFAC, so I have a PFAS project in Guam. Looking forward to Dr. Kim's presentation.
Wonderful. Aloha. Um,
Aloha.
yes. Wonderful. Okay.
Robertson
Eh,
with AECOM. I work with Linda Wen.
Thank you.
Alpha Day, my name's Ariana. I'm a policy analyst with Senator Sabina Perez.
Thank you.
Hi, my name's William Janisak, and I am a senior engineer for EA Engineering here on Guam.
Wow. Wonderful. Thank you.
Hi, everybody. Brian Bearden with BECQ up in CNMI, formerly with Guam EPA the previous 5 years.
Wow. Half a day from Saipan. Very good, very good. Are we done?
No, we have one of our engineers, Jessie, from GWA. She's one of our engineers working on water resources as well.
Good afternoon.
Hey, Jesse, you say something?
I work with the water CIP team at GWA Engineering.
Well done. Thank you. Thank you. Okay, folks, I think we are all in the house. And again, thanks to everybody. We'll have a few minutes towards the end. And I think Dr. Kim will run you until 3:45 or so, where we can entertain some questions. Is that okay?
Okay, so
all right. So let me just quickly introduce Dr. Kim is an associate professor here at the University of Guam under the Water and Research Institute, that's WARI, here in the Western Pacific. He joined UOG in 2019 as assistant professor. He's currently now the associate professor, and he did his PhD in civil engineering, Purdue University. That's 2008. So he's been teaching quite a number of courses here: environmental engineering, geoscience engineering, hydrogeology, and remediation engineering. And he's been doing quite a few work here in the water quality and also the water system here in the in Guam and in the region. So without further ado, Dr. Kim, welcome. Good afternoon. Floor is yours.
good. Thank you, Dr. P, for introduction. Thank you for invitation to ALS 691 webinar series. So my name is Barry Kim. I'm Associate Professor of Water Engineering at Raleigh University of Guam. And today I will present one of my research topics, the impact of per and polyfluoroalkyl substance, PFAS pollution on Guam water resource. Yeah, I will proceed with this presentation in the following order. So what is PFAS? The source of PFAS pollution, PFAS contamination status in Guam, and my study, well, 825 PFAS source attribution study, and preliminary analysis of UCMR5 PFAS data. And at last, I will introduce my concern and future research. Okay, then what are PFAS? PFAS are a class of synthetic chemical characterized by strong carbon-fluorine bonding. So if all carbon atoms are fully saturated with fluorine, except to the main carbon-carbon bonding, then compound is classified as PER. And if some carbon bonds are substituted with hydrogen, chlorine, or some other atom, then it's classified as poly. PFAS are commonly referred to as forever chemicals due to their exceptional resistance to degradation. So numerous PFAS compounds have been linked to adverse human health effects, and they are also classified as potential carcinogen. PFAS are synthetic chemicals, so meaning their presence in the environment is the result of human activity. Today, more than 6,000 PFAS compounds and their derivatives have been identified in the environment. Major sources of PFAS contamination include aqueous film-forming foam, we usually call AFFF, used in fire suppression, as well as non-stick cookware, textiles, furniture, and various industrial and consumer products. PFAS compounds can vary in carbon chain lengths and functional groups, so which influence their chemical and physical properties and their behavior. For example, PFOS contains a sulfonic acid functional group. The nomenclature of PFAS follows standard organic chemistry conventions. So, for example, the terms such as butane denote 4 carbon chain, and decane represent a 10 carbon chain. As I mentioned before, PFAS display a range of physical properties. One such property is water solubility. So according to literature review, the aqueous solubility of PFOA is about 9,500 milligram per liter, and PFOS is 680. In general, PFAS compounds with lower molecular weight tend to have higher solubility compared to those with higher molecular weight PFAS. The second physical property I want to introduce is ionization in aqueous system. PFAS can exist as anionic, cationic, or in some cases as deuterionic species. Deuterionic PFAS contain multiple functional groups, which enable them to behave as either cation, anion, or both, depending on pH, temperature, or other ionic condition of the surrounding environment. The third physical property I introduced is the ability to form micelle. When the carbon chain length exceeds 6, the PFAS molecules can organize into structures with a hydrophobic tail and hydrophilic head. And next, I want to address the sorption behavior of PFAS in soil layer. Similar to other organic pollutants, PFAS tend to absorb to organic soil. However, organic soils possess a net negative surface charge, which can increase the affinity for cationic PFAS. So that can lead to distinct sorption behavior for different PFAS compounds. In the case of limestone layer, this surface can carry both positive and negative charges. As PFAS move through the limestone layer, there is a potential for interaction with each other and adsorption process can occur. However, there is currently no available data on sorption behavior of PFAS with Mariana and Vargada limestone target on Guam and Saipan. So the detail of this sorption process remain unclear at this time. And next, so let's examine the soil water partitioning coefficient, or we call KD. KD is defined as the ratio of the concentration of a specific PFAS in soil to its concentration in water. This coefficient indicates the relative affinity of PFAS for soil versus water. In general, PFAS with light or molecular weight tend to dissolve more readily in water than in soil. In summary, so a wide range of PFAS compounds exceeding 6,000 are present in the environment. Many of these compounds are recognized for their potential adverse effect on human health. PFAS are extensively used as a key component in numerous industrial and consumer products. The physical properties of PFAS, such as water solubility and soil sorption, are primarily determined by their ionic characteristic, carbon chain length, and molecular weight. However, these interactions are complex and influenced by various factors. Okay, then now let's move on to the primary source of PFAS contamination and their associated pathway. The primary sources of PFAS contamination include firefighting training sites, fire incident locations, and AFFF storage facilities. The area that handle AFFF are often identified as a major contributor to PFAS contamination. Another main source of PFAS contamination includes landfill and dump site. Especially, landfill release leachate, which can directly contribute to groundwater contamination. And also, the improper management of stormwater runoff surrounding landfill and dump site can cause surface water pollution. And also, improper management of wastewater station or discharge system can directly lead to PFAS contamination. And also, biosolids are primarily associate with soil pollution, but they can contribute to water pollution as well. The US EPA outlined the primary source of PFAS in the 2023 EPA Federal Facilities Superfund Program report. In addition to these key sources, the maintenance shop and munition areas are also recognized as significant PFAS contamination sites. In addition to non-PFAS contamination sites, the non-point source pollution, such as stormwater drainage, ponding basin, rivers, and swamp, should be investigated if the PFAS source remain unidentified. Okay, then how about Guam? The release of PFAS typically begin at the topsoil layer or through open water channels. Once released, a significant proportion of PFAS remains in the topsoil, particularly in organic soil. The next stage involves migration through the thick limestone vadose zone, following the pore water flow until it reaches to groundwater. Once PFAS reach the aquifer, they move with the groundwater flow and then eventually flow toward a coastal area. The detection of PFAS in drinking water source in northern Guam indicate the result of PFAS traveling from the topsoil layer through thick limestone. Therefore, without identifying the surface level source of PFAS, it is nearly hard to accurately trace the source of PFAS detected in groundwater. Regarding PFAS migration, there are three possible scenarios. The first is long-term retention in the topsoil. According to the literature review, PFAS can remain in organic soil for several decades. And the second scenario involves rapid movement into the aquifer via preferential fast water flow pathway. And the third scenario is a slow movement through the compacted limestone layer. Okay, and now let's address the actual PFAS contamination issue on Guam. Before I begin, let's briefly review the timeline of PFAS monitoring and EPA regulation. PFAS were first discovered in 1930s, and by 1970s, they were detected in human blood. In 2009, the US EPA established provisional health advisory level of 400 nanogram per liter for P4 and 200 nanogram per liter for P4s. Between 2013 and 15, all US public water agencies monitored 6 PFAS compounds under UCML3. In 2016, the EPA announced a new health advisory level of 17 nanogram per liter for P4 and P4s combined that recommend public water agency to take action. In 2023 and 24, the EPA required all public water agencies to monitor up to 29 PFAS compounds under UCML5, with the first round of monitoring covering approximately half of water system on Guam. In April 2024, the EPA established new PFAS regulations for 6 PFAS compounds, implementing more stringent maximum contaminant level, with some as low as 4 nanograms per liter. In October 2024, EPA released the result of the first round of PFAS analysis to the public, and the second round sampling is currently ongoing. This ongoing monitoring is expected to be completed by April 2027. Beginning in April 2029, all public water agencies must comply with the new PFAS regulations, meaning that any water systems exceeding the established MCL must implement solutions to reduce PFAS levels below regulated regulatory limit by early 2029. And this slide presents the result of UCMR3 monitoring conducted in 2015 by GWA. Among approximately 120 production wells, 6 Guam's wells were found to contain PFAS, PFHXS, or PFHPA. In addition to this, 3 wells, NAS-1, A23, and A25 exceeded MCL, and PFAS was the most frequently detected in Guam. After the closure of these 3 wells to comply with the EPA regulation in 2016, a granular activated carbon, we usually call GAC filtration system, was installed at NAS-1 well, which is now back in operation. However, 2 other wells, A23 and 25, remain offline. So last month, GWA announced that about 10 million will be allocated to install GAC filter system at A23 and A25. Okay, now let's discuss my PFAS study in Guam, which focused on source distribution for wells A23 and A25. So this study was funded by National Institute of Environmental Health Science and supported by STEP grant in collaboration with the University of Rhode Island. The starting point of this research was the unknown source of PFAS detected at well A25. The hypotheses were as follows. PFAS contamination may be originating from nearby site. PFAS initially impacted in the surface soil or sediment. PFAS detected at well A25 could be the result of migration through surface water and groundwater flow. And PFAS, along with their degradation product, may still persist in the soil, organic soil layer. And this slide illustrates the drawdown of water table caused by well operation. If the groundwater flow is very gentle, then groundwater from both upstream and downstream areas can move toward the well during its operation. Based on this idea, we analyzed both surface water and groundwater flow in relation to the geology of this region. And we identified 2 potential major sources of PFAS. One is the ponding basins in Agania High, upstream of groundwater flow, and the other is Agania Swamp. Since Agania Swamp interact with groundwater, the surface water in Agania Swamp can also be a significant source of PFAS. So in this study, we chose a total of 34 PFAS compounds for the analysis. So this compound covering all 6 from UCMR3 and about 25 out of the 29 PFAS compound for UCMR5. So the first suspected site was the 4 ponding basins in Agania High because they serve as primary route for groundwater flowing upstream of well A25. The second suspected site were located near well A25, including the stormwater drainage near the Agania Shopping Center and Agania Swamp. These areas are close to well A25, and there was evidence of spraying firefighting foam at Agania Shopping Center parking lot during fire prevention week in 1980s. The third suspected site was the Trout River upstream near the GWA wastewater pump station, which has a history of long-term wastewater leakage. Although this pump station was not directly related to well A25, the Trout River is directly connected to Agania Swamp. So we included this site as a potential PFAS contamination source. And lastly, the Ponte River was also considered a potential PFAS. In 1997, the Korea Air Image Hill, and we suspected the use of firefighting foam in this area, which is directly connected to the Ponte River. While there is no documented evidence of firefighting foam use, we included this site in our study due to potential concern. So after these potential PFAS contamination sites were decided, and we selected a total of 22 sampling locations. At each location, we collected the soil or sediment sample, and as mentioned earlier, we analyzed a total of 34 PFAS compounds. As a result of PFAS analysis, 33 out of 34 PFAS compounds were detected in the soil and sediment sample. This was an impressive result, as all the sample contained various PFAS compounds. In addition, Ponding Basin A1 near well A25 showed the highest level of PFAS. PFAS is a primary ingredient in firefighting foam, so it is still unclear why PFAS level is so high at Ponding Basin A1. And this analysis also revealed that the wastewater leakage area can be the main PFAS contamination source, showing the highest level of various PFAS compounds. And in this PFAS analysis, PFOS, PFNA, PFHXS, P4, PFDA, 62FTS, and HFPODA, known as GenX, were detected at the highest level among all samples. And most of the PFAS detected at high level were also found at a very high frequency in all soil samples, except for PFOS. So what could be the reason for the relatively lower detection frequency of PFAS? This slide presents an example of PFAS analysis in soil sample we collected from the Saipan firefighting training area. So historically, 3M brand AFFF was widely used as a firefighting foam, with PFOS as its primary PFAS ingredient, and reaching concentration as high as 7,900 milligrams per liter. This PFOS concentration is at least 10 times higher than that of any other PFAS compound in 3M AFFF. So therefore, PFOS detection serves as a strong indicator of contamination from PFOS-based AFFF. In addition, the localized presence of PFOS can provide valuable evidence of past AFFF use, even if it occurred a long time ago. There are two main types of AFFF. For fluoropolymer-based AFFF, the presence of 6,2 and 8,2-FTS can serve as an indicator of AFFF contamination. However, this approach requires caution because many other potential sources of PFAS exist. So therefore, if AFFF-related PFAS are detected at a site without clear evidence of AFFF use, alternative sources should also be considered as a potential contributor to contamination. Okay, now let's discuss the advanced statistical tool used for PFAS source attribution analysis. And my questions regarding the PFAS analysis data were, how can we categorize both PFAS compound and potential contamination site based on similarities and differences in their detection pattern? As you have seen in the presentation, the PFAS research is highly complex and requiring more advanced analytical tools to develop effective solutions. To address this challenge, our research team employed multivariate analysis technique, including principal component analysis, data correlation analysis, and cluster analysis. These methods are particularly effective for identifying correlations between PFAS compound and potential contamination source. So before applying statistical method, we refined the sampling site to focus especially on the well 825 area. So we selected 17 sampling spots for the statistical analysis. And this slide shows the correlation matrix among all 33 PFAS compounds detected at 17 sampling spots. The advantage of this correlation analysis is that it provides insight into which compounds are likely to be detected together at each sampling spot. So here's an example. The main fluorotelomere PFAS A2FTS shows high correlation with PHXSA, PFDS, and PFPEA, which are the primary component of AFFF. And PFOS also show a high correlation with PHXSA, PFHPS, and PFPEA, which are key components of AFFF. So these are a good indicator of identifying AFFF contamination site. But PFOS shows a high correlation with PFHPA and PFODA. So PFOS correlation pattern may differ a little bit from that of primary AFFF PFAS component. And this slide presents the dendrogram generated using hierarchical cluster analysis. So this analysis groups PFAS compounds based on the similarity of their detection pattern. The results show patterns similar to those observed in the correlation matrix approach. So this analysis suggests that the co-detection of PFOS, PFDS, PHXSA, A2FTS, PFHXA, and PFHXS, and PFPEA is likely the key indicator for both PFOS-based and fluorotelomere-based AFFF contamination. And this slide presents the result of principal component analysis to identify the similarities among each sampling site. The interpretation of the piece A result is based on confirming the direction and length of the arrow. There are other complicated processes to evaluate, but I will not introduce them today. So, for example, if arrows point in the same direction, it indicates that the site shares similar PFAS contamination pattern. The length of the arrow represents the reaction intensity. That means longer arrow indicate higher level of PFAS. As shown in this slide, site 13 and 14 shows similar PFAS contamination trend. And site 13 is the stormwater drainage near the Agania Shopping Center, so where the fighting foam was sprayed in 1980s. And site 14 is a ponding basin upstream of the groundwater just behind well 825, so where PFOS was detected at the highest level. And the site 4, the wastewater leakage site, is located in the first quadrant, indicating that its PFAS distribution pattern differ from those of site 13 and 14. However, since site 4 and 13 and 14 are all show positive value along the x-axis, that means some similarities still exist among them. And this slide presents the result of hierarchical cluster analysis that integrate data from 33 PFAS compounds and 17 sampling sites. The analysis identifies site number 4, the wastewater leakage site, and site number 14, ponding basin with the highest detected PFAS level. So because the most significantly PFAS contaminated location. And in addition, site number 13, stormwater drainage area near the Aganya Shopping Center, also shows considerable correlation with site number 4 and 14. However, the clustering analysis result shows that the site number 13 was not grouped with site number 4 and 14. That is possibly due to its relatively low PFAS concentration, likely influenced by continuous water flow that disperses contaminants to other areas. Anyway, so overall, these findings highlight the effectiveness of cluster analysis in identifying heavily contaminated PFAS sites and in grouping location with similar contamination patterns. So based on statistical analysis, the likely scenario for PFAS migration into groundwater at well 825 involves contamination originating from the Aganya High ponding basin and the stormwater drainage area near the Aganya Shopping Center. And this research has some limitation and possibility as outlined below. The number of PFAS sample is relatively small for robust statistical validation. That was the weakness of this research. But if we can expand the analysis to include up to 10 or 200, 100 or 200 PFAS compound, then we can enhance predictive accuracy. In addition to this, if we conduct soil sampling at different depths, then data collected at different depths can provide more detailed insight into PFAS distribution patterns. Nevertheless, this approach offers valuable insight into identifying non-point PFAS sources using statistical tools and determining the primary source of PFAS contamination in well area. Okay, then let's move on to the current PFAS contamination status in Guam, focusing on UCMR5 semi-result. In October 2024, US EPA released open source data, including the first round of UCMR5 PFAS monitoring. So this slide presents the EPA's PFAS GIS map covering entire region of the US. So you can visit this website. And you can also download data for all US water systems, including Guam and Saipan from the EPA website. And UCMR5 data is also available for direct download from this site, as shown on this slide. In compliance with regulation, GWA publishes an annual water quality report. The 2023 GWA annual report is available on the GWA website. And this report includes 2023 PFAS data measured at GWA well. Under the first round of UCMR5, a total of 62 water systems, approximately 50% of Guam's water systems were tested. And of these 62, 58 were GWA production well, and 4 were Anderson Air Force Base water system. And sampling was conducted between 2023 and 24 with 1 or 2 samples taken from each well. I will now present the detailed contamination status of each well, along with the UCMR5 PFAS data. So once the second round of UCMR5 sampling is completed in 2026, the annual average values from all samples at each well will be used to determine whether a maximum contaminant level are exceeded for each well. However, since we currently have only 1 or 2 samples for water system, in this analysis, I selected just 1 sample at each well, showing the highest summation PFAS concentration to access potential MCL exceedance. So therefore, I want to mention that this preliminary result may differ slightly once all UCMR5 data is available in 2027. Out of 58 wells, 37, about 81% of the tested well contained at least 1 PFAS. And 1 of the 4 airflow water system also tested positive for PFAS. A total of 26 wells, about 44% of the test well exceeded maximum contaminant level for at least 1 regulated PFAS. All 3 wells monitored in Havana and Manguilao exceeded MCL, indicating that at this time 100% of the monitored 100% of tested well will violate PFAS regulation, unless PFAS levels are reduced by 2029. And also, 4 wells in Barigada and 6 wells in Chalampago Odo exceeded MCL. And this slide displays 6 regulated PFAS along with their minimum reporting level and maximum contaminant levels. Among 29 UCMR5 PFAS compounds tested, the 11 PFAS were detected in Guam. In addition to this, PFAS analysis data show that 5 PFAS among 11 detected PFAS are regulated PFAS compounds. The hazardous index formula includes 4 regulated PFAS, and this formula uses annual average values for this calculation. So far on Guam, as I mentioned, 2 regulated PFAS, PFBS and PFHXS, are relevant for the hazardous index calculation. So since I selected only 1 sample for this estimation, the hazardous index I calculated may differ slightly compared to EPA's calculation. So this slide shows GIS map for all monitored production wells during the first round of UCMR5. The red color indicates wells exceeding MCL, at least 1 regulated PFAS. Green represent well exceeding minimum reporting levels, and white dot indicate well where no PFAS were detected. As shown on this map, most well exceeding MCLs for at least 1 regulated PFAS are concentrated in Havana, Chalampago Odo, and Manguilao. And this slide shows the total concentration of detected PFAS at each well. As seen on the map, the highest total PFAS concentration was detected at NAS1 well, followed by Y15 in Jigo and A9 in Chalampago Odo. So as I mentioned earlier, most of the PFAS contaminated wells were concentrated in the middle of Guam. But at this time, we do not know the exact reason for the high concentrations in this well. So one possibility is that groundwater flow in this area is much slower compared to other sub-basins, which could contribute to long-term contamination. So this site may be an interesting area for future organic pollutant research. And this slide shows potential boundary that need to be investigated for a localized PFAS contamination based on UCMR5 data. This slide shows several example newspapers regarding estimated PFAS contaminated well on Guam and the projected cost associated with addressing PFAS in water system. The GWA estimate that around 34 well may require a treatment system to reduce PFAS level, with cost potentially reaching approximately 100 million. So as I mentioned earlier, the GWA also plans to spend about $10 million to install gas filter for 2 wells, 823 and 825. And currently, we are focusing only on PFAS detection in the drinking water system. However, as we have seen from several slides on groundwater PFAS contamination, Guam's groundwater eventually flow toward the coastal area. So this suggests that the coastal area and benthic ecosystem may be impacted by PFAS, although we do not have any data, especially targeting the coastal area at this time. So, and also if you Google military base Guam and PFAS, you can easily find PFAS monitoring related report and tasks conducted by NEFEC. This slide shows an example of what I found online regarding native PFAS-related activities. The military initially began identify potential PFAS contamination site using soil sampling. And they are now monitoring PFAS in their water system and installing monitoring wells for PFAS detection. So, what is my concern about PFAS on Guam these days? All U.S. public water agencies are trying to reduce PFAS in their water systems before the new PFAS regulations is applied in 2029. And that's exactly what GWA is doing its best to address. In addition to this, most U.S. state governments are securing funding to identify PFAS sources because this task is not typically the responsibility of public water agency. And in my case, I'm preparing research proposal to acquire grant, but generally competitive grant funding is limited to only cover 2 or 3 well sites. As you know now about my research, I focused on well 823 and 25, which is a typical case for researchers who can conduct study with research grant. But now, with UCMR5 data showing that Guam's groundwater is widely contaminated with PFAS, my question right now is, who will take responsibility for identifying PFAS sources across the entire region of Guam? So in general, PFAS research on Guam requires significant funding because PFAS analysis can be quite expensive. In addition, government agencies play a crucial role in this work, as it is not only related to research and regulated compliance, but also to managing potential risk. To move forward, it is essential to collect historical documents such as contamination histories and the location of chemical storage in order to identify potential contamination sources. Government agency can provide this information. So as far as I know, some former politicians have worked to secure PFAS-related funding. For example, in 2017, former Senator Bob Cristobal proposed a $7 million research for health study for Guam. And in 2022, former Speaker Judith Wompet raised concern about PFAS contamination in Guam's drinking water and emphasized the need to secure better funding for PFAS research. So as we know, the UCMR5 data was released 5 months ago. So now is the best time to begin discussion about PFAS issue with stakeholders and get ideas and secure funding for PFAS study. And this slide is the last slide for my presentation. So this slide presents a research design concept for identifying primary PFAS sources and non-point source PFAS contamination area in relation to PFAS contaminated well. As mentioned earlier, PFAS sources include firefighting stations, airport, harbor areas, wastewater treatment facilities, and munition sites. By collecting all samples and analyzing up to 100 PFAS compounds from known PFAS contamination sites, we can develop a PFAS library that links specific PFAS signatures to their respective sources. And furthermore, this PFAS library can be utilized to identify previously unknown contamination areas by leveraging advanced statistical tools and existing PFAS datasets. In late January, Guam EPA invited me to present on Guam's PFAS issues. During the meeting, I shared my assessment that conducting soil sampling and this type of analysis to investigate PFAS contamination across the Guam would require approximately $3 million in research funding. So I hope this discussion will continue to progress actively in the future. So in this research, many team members have contributed to PFAS research. So Ms. Mallory Duenas, now very laboratory manager on her master's degree through the study on PFAS contamination in Guam. And Mr. Aaron Marijo, now a researcher at Silent Spring Institute, worked as a summer intern for PFAS study while pursuing his master's degree at UC Berkeley. And Mr. Julius Bonapescio, currently an engineer at GHD, contributed to statistical analysis of PFAS data. And Ms. Claire and Ms. Mary, very research assistant, assisted in collecting library information and GIS data. And Dr. Nate Havana, associate professor at Very, supported the groundwater flow analysis. And Dr. Rainer Lohmann, professor at University of Rhode Island, collaborated with me to share research, PFAS research trend and be a co-author papers. And Dr. Gita Bekanova, research professor at University of Ireland, she is assisting for PFAS analysis. And thank you for listening my presentation. And if you have any questions, please feel free to contact me. Thank you again, and feel free to ask if you have any questions. Thank you.
Thank you so much, Dr. Kim, for that very, very thorough and informative presentation. Now we'll open up for any questions in this next 5 minutes or so. Please go ahead and bring up your questions.
This is Dr. Weir. I have a couple of questions that I've directed to the speakers, if they could look at the chat.
Okay.
Yeah. I need to check the data, but we analyzed a soil sample. So summation of PFAS level will be lower than 3 microgram per kilogram dried soil, but it is not accurate data because I need to check my raw data.
Sorry, can you read the question? Because I don't see it in the chat.
What PFAS levels are noted at the outflow of Aganya River and the Aganya municipal site?
Okay. Thank you. Next question.
Can I ask, Dr. Kim, did you say that you think that 825, can I just confirm what you're saying? You feel that the source of that PFAS coming from the Agana Heights Ponding Basin and the storm drain from Agana Shopping Center?
Yeah, based on my analysis, so I really suspicious ponding basin just behind of A25 because we detected the highest PFAS level. So currently we don't know why PFAS level is so high to this ponding basin. And also, some people know about Fire Prevention Week at the Agana Shopping Center. And then that area was a paved site. So what I suspicious was firefighting foam flowed toward the stormwater drainage, and then some of PFAS percolated into groundwater. That's my guess. But as I mentioned before, we only collected 22 soil samples. So I think to confirm this research, we may need to more intense the research to take more sample and also with different depths.
This is Dr. Weir. Should be noted that the Agana Swamp is right adjacent to those areas.
Right.
Thank you. Any further question?
I have a question for Professor Kim.
Go ahead.
For a personal action, what can us residents and students can do to reduce PFAS exposure?
Well, so if you Google, you can find which product include PFAS. So you can avoid any product which can contain high level. I think that is the way we avoid PFAS at this time.
Okay, thank you so much.
Yeah.
So my question, Dr. Kim, is in terms of the analysis of PFAS, do we have the capability here on island to carry out those analytical work that provides the data for this research?
So to analyze the PFAS, we need to have high resolution mass spectrometry. But unfortunately, still on Guam, we don't have that instrument. So as far as I know, Guam EPA is going to purchase that instrument. So once we have that one, then we can expand our PFAS research very quickly. But it will take time, I guess. Still, that means we still have a big limitation for PFAS research on Guam.
Thank you. All right. Any final question before we move a vote of thanks to our speaker today?
This is Dr. Weir. One further question. If your lab had that machine, would you be able to operate it?
Yeah, I think we can, but it will take time to train a laboratory staff. But if we have, then that is a time issue, but we can eventually operate that machine.
Yeah, just to follow up on that question, the chemistry department has already acquired a GCMS, so most of our students are getting more and more hands-on experience in the instrument using the mass spec detection system, which is the more advanced method of working with these PFAS compounds. All right. I think that's probably will wrap up our meeting this Friday. It's getting into the weekend. So on behalf of the AL 691 team and for us here at the College of Natural and Applied Sciences, I would like to thank our speaker today, Dr. Kim, for starting the series. And it was a great success with all the friends and those who are interested joining us from here and even across the region and even beyond. So with that, I'd like us to give a round of applause, electronic applause, I guess, to our speaker today and for the very well presented talk. So thank you, Dr. Kim, and thank you all. Wish you well and have a good weekend. And our next talk is going to be also coming up through the website and distribution, so keep an eye on that. But meanwhile, thank you so much and wish you well. Thank you.
Yeah, thank you all for joining. Thank you so much. Have a great weekend.
Thank you, Dr. Kim. Have a great weekend.
Yeah, thank you.
Thank
Yeah.
you.
Thank you. Bye.
Thank you. Take care. Bye.
Yeah, Dr. Puki, you can stop recording.
Okay, I'll stop recording now.